Have you ever wondered how it is that we know which compounds we have? We see all these bond line structures drawn all over the place in this class, but for a moment, did you question how is it that we know that these atoms are connected in this particular way? Well, it turns out we do know, and the way that we know is using a process, series of techniques really, called spectroscopy. We study the interactions of molecules with light. So as you can see, this sort of introductory slide kind of asks the same question. How do we know what molecules we have? We study those interactions between matter and light, and this is called spectroscopy. Now, we cannot take a photograph of a molecule. If you zoom in with a super camera and try and take a picture of a molecule, you will fail every time because the wavelength of light is larger than that of these teeny tiny molecules. So you'll never be able to reflect light off of a molecule in order to get a photograph of it. It's just not possible. How can you take a picture of something smaller than the wavelength of light that you're using to photograph with? So it's not photographs that we're taking here. Instead, we are trying to understand how light can interact with molecules in other ways. And so the key relationship is the energy of a photon formula, which says that energy is equal to Planck's constant times the speed of light divided by wavelength. You could also say that energy is equal to Planck's constant times the frequency of light. Now, because Planck's constant and the speed of light are both constants, that means that energy is inversely related to wavelength. That means that the smaller the wavelength of light, the higher energy the photon is of that light. And so I want to now list some types of light, which are sometimes called electromagnetic radiation. So I know that word is scary, radiation, but in this context, when we talk about radiation, we are not talking about nuclear radiation. We are talking about electromagnetic radiation, which for most intents and purposes, except for the very high energy forms, is completely harmless. So, for example, if the wavelength is 10 to the 9 nanometers, so that's a very long wavelength, that's a very high number, the energy of that light is going to be very low. And we call that light radio waves. So I'm going to just kind of fill these in here. So, and you don't need to memorize these at all, but it would be helpful to know the order of these types of light. And so one of the lowest energy forms of electromagnetic radiation is called the radio wave. And if you shine radio waves at a molecule, what is going to be the outcome of that? Well, something called a nuclear spin flip. That sounds kind of silly. It sounds almost scary. Is it some sort of nuclear gymnastics? No. This is a very, very minor change you can barely detect. It's basically the particles inside of the nucleus, things like the protons, they can undergo a flip, a spin flip. So you change their sort of angular momentum. Very small change. You can hardly notice that on the outside. So it's really not doing much to a molecule at all. If you shine 10 to the 6 nanometer light, which is slightly more high energy, we call that microwave light. And we're all familiar and we all love our microwaves, don't we? Because when you expose a molecule to microwave radiation, it causes molecular rotation. It causes the molecules, the bonds inside, to start rotating, and that can create some thermal energy. So that's how microwaves heat up your food, is they cause the molecules of water inside your food to start rotating. That applies thermal energy because we know that molecular motion is directly connected to thermal energy, and so that's going to cause the sample to heat up. So that's how a microwave warms up your food. But really the outcome is not all that scary. It's just causing the molecules to rotate. It's not destroying the molecules or breaking the molecules. It's just rotating the molecules. So again, pretty low energy light, pretty harmless what it's doing. Infrared is the next highest energy. Infrared light, and that's actually going to be the topic of this lecture, causes molecular vibrations. So similar to rotation, it's going to cause now the bonds to start vibrating. Again, that applies thermal energy. So if you shine infrared light at a sample of organic compounds or any molecules, they're going to start vibrating, they're going to start heating up. And so actually, if anyone here is a reptile owner, you may own an infrared light for the reptile enclosure. That's going to provide some nice warmth for your iguana or your snake. Let me know if you have a reptile. That's pretty cool. They're kind of scary. I do not have a reptile, but I'd be interested to know if you do. 500 nanometer light. That is, now we're in the visible region. So this is the light that we know and love, visible light. And if you shine this at a molecule, it does something called an electronic excitation. And we've actually already seen this in the conjugations lecture. We saw that if you shine a photon of light that's equal to about the HOMO-LUMO gap, it can cause an electron to become excited to the LUMO from the HOMO. And so we've already seen these electronic excitations, where electronic is referring to electrons being promoted to higher energy states. And so we saw that because of this electronic excitation in the conjugation chapter, that was helping us explain why some highly conjugated compounds appear to have a color. And that's because they're absorbing visible light to cause these electronic excitations. Above visible light comes ultraviolet. And now this is where electromagnetic radiation starts to become quite harmful to our bodies. Ultraviolet light also causes electronic excitations. However, because this is a higher energy light, it's able to interact with molecules that have a relatively large HOMO-LUMO gap. Remember, as we increase conjugation, the HOMO-LUMO gap gets smaller and smaller and smaller. But with ultraviolet light, since it's a pretty high energy light, it can cause electronic excitations in molecules that are not conjugated, that are just normal, which have very large HOMO-LUMO gaps. So when you start creating electronic excitations in molecules that aren't conjugated, you start widely affecting molecules in your body, like proteins, and causing damage to those proteins. So that's why being exposed to ultraviolet light is always a bad idea as a person. So like, for example, you probably would want to stay away from a tanning bed, because that is going to be exposing you to ultraviolet light. Now keep in mind that that's relatively low energy ultraviolet light. If I actually exposed you to high energy, or like more towards the higher end of the electromagnetic spectrum, ultraviolet light, you would cook very quickly. It would not be a pretty picture. But of course we know the sun causes us to get a sunburn, and that's due to the ultraviolet light causing electronic excitations in our proteins. So avoid the sun as best you can, because the ultraviolet radiation is not good for us. Next up, we have the X-ray. Now these are very harmful. X-rays you do not want to be exposed to. Unfortunately, we do get exposed to X-rays a little bit every time we go on an airplane. There's a little bit of X-ray radiation. That's why pilots have a higher incidence of cancer, because they're exposed to more X-rays. X-rays, of course, being produced by the sun, and they are shielded mostly by the atmosphere, thankfully for us. If it wasn't for that protective atmosphere layer, we would all be cooked by X-rays from the sun. Another reason why you would not want to go to Mars, the atmosphere on Mars is not very protective against X-rays. So if you hang out on Mars, you will be cooked by X-rays. Now, X-rays are useful to us. We use them in a medical field to help image our bones and look inside of our bodies and see those tissues. However, being exposed to X-rays for more than a minute or so is going to cause serious damage, because the outcome is ionization. Ionization means that it excites electrons out of the orbitals. So not just exciting them to higher energy orbitals, but exciting them completely off of the molecule. And when you start removing electrons from molecules, you create charged ions. Charged ions can interact with other molecules in your body and cause severe damage. So for that reason, X-ray radiation causes very bad burns if you're exposed to it for more than a few seconds. That's why when you go to like the dentist and get some X-rays of your teeth, they flip the switch only for like a split second, and they expose you to the X-ray, but you probably should not be exposed to it too many times per year. And finally, the highest energy form of light that we define is called gamma ray. The gamma ray is sometimes called cosmic rays. They're produced by stars. It's a very high energy form of radiation. You definitely do not want to be exposed to gamma rays. It's also released by nuclear bombs. The result of this would be bond cleavage. So this ejects electrons out of the bonds that holds molecules together and causing the molecules themselves to be disintegrated. You can imagine this would have a very, very dangerous effect on the human body. But even though we're talking about all these interesting types of electromagnetic radiation, we're mostly interested in the infrared light for this part of the class. All right, so here's another picture representation of the electromagnetic spectrum, and you can see the lower energy light is over on the right, and the higher energy light, the gamma rays, is over on the left. And interesting to note that the visible spectrum is a very, very narrow region of the spectrum. We can only see a very, very narrow region of light, and that's actually a good thing. If we could see all the different types of light, we would be completely blinded with information. For example, your Wi-Fi router right now is ejecting light in the microwave region. You would not want to see all the light that's being emitted by your router giving you Wi-Fi. Otherwise, it would be very difficult to see your way around your house. Okay, so it's a good thing that we're only able to see the visible light, since that's the region that's most useful to us. Okay, so what is this about IR spectroscopy? What is the concept here behind IR spectroscopy? We know we're going to be shining IR light at molecules, and we know that IR light causes vibrations. How is that going to help us figure out what molecule we have? So here's the concept behind this technique. The concept is that bonds vibrate when exposed to IR light. Okay, why do they vibrate? Well, let's take a look at what exactly is IR light. IR light is just electromagnetic radiation. If you look at what electromagnetic radiation is, it is a wave of energy. And it's the wave contains an electric field. And I'm sorry that my wave kind of sucks, but imagine my wave is a little bit more symmetric. And the wave contains a magnetic component and electric component. That's why it's called electromagnetic radiation. So let's just say for a second we're looking at only the electric component of this wave. And so as it oscillates, you have areas with positive charge and areas with negative charge. And so the wave is sort of oscillating through space, positive, negative. That is what light is. So it's this positive, negative electric field. And let's say this light navigating through the universe strikes upon a molecule like this, for example. Acetone. Beautiful molecule, beautiful ketone, used as nail polish remover. So it's beaming through the universe, hits that molecule of acetone. What is going to happen? Well, it turns out that this molecule of acetone is a polar bond in it. The oxygen has a partial negative charge because it's an electronegative element, and the carbon has a partial positive charge because it's an electropositive element. So that means this bond is polarized. The bond is polarized, and so it has a positive side and a negative side. Well, we know that an electric field can interact with another electric field, and this molecule is generating a mini electric field by virtue of the fact that there is this charge separation due to the polarity of the bond. When the wave hits this molecule, if it's the right wavelength, it's going to align with the plus and the minus, and it's going to stretch the bond. The minus side may stretch the positive side a little bit down, and the positive side may stretch the negative side a little bit down, because we know that positive and negative attract each other. So what's going to happen is, I'll kind of just draw a little equilibrium arrow, is that it's going to cause the bond to stretch. And so I'm going to draw it really long now to show that the bond got stretched by the application of this electric field. So we'll just have a little comment here that light has an electric field. So it can interact with polar bonds and cause them to vibrate. So let's take a look, though, at a consequence of that, and that is that IR light can only interact with polar bonds. So let's compare two scenarios. Let's say we had a nonpolar bond. For example, this alkene. We have a pi bond in there, that double bond in the middle, but it's not polar because it's connected to two carbon atoms on either side, and so there's no difference in electronegativity between two carbon atoms. The difference in electronegativity is going to be zero because they're the same atom. So what that means is when the IR light comes by, it's just going to go right through, and it's not going to be absorbed by the polar bond because there is no polar bond. So we call this kind of molecule IR inactive, meaning that there's no change in the dipole upon vibration. In other words, the IR light is just going to pass right through it. There's no dipole, there's no charge separation. So this molecule, for all intents and purposes, will be invisible to IR spectroscopy. You won't be able to see it. However, if we start having polar bonds, and the more polar, the better, then this would be IR active. The IR light comes by and boom, it gets absorbed by the polar bond and then can't go through anymore because the energy of that wave is absorbed by the bond vibrating. So that energy has to go somewhere and it goes into making the bond vibrate. So you shine the infrared light at the molecule and it doesn't come out the other side. So this would be called IR active. Now here's the fun part. Different bonds have different strengths. And also vibrational modes. Vibrational modes just means they can vibrate like this, or maybe they vibrate like this, different ways to vibrate. And so they absorb light. They absorb IR light at different frequencies. You can imagine if the bond is really strong, it's going to take more energy to cause it to vibrate, which means the amount of IR energy that you need is going to be higher. So by detecting the slight differences in these frequencies that are absorbed, we can kind of figure out an idea of what types of bonds are inside of a molecule. Let's take a look at what an actual IR spectroscoper looks like. It looks a bit like a toaster, a very expensive $10,000 toaster with a lot of warnings all over it because it uses an IR laser. How does it work? Like I said, there's an IR laser, which in this schematic diagram is labeled as IR source. The IR source is split using mirrors that cause the IR laser to travel down two paths. In the top path, the IR laser passes through the sample. In the bottom path, the IR laser passes through a reference sample. The reference sample is usually made of, it's just an empty container that's made of the same material that the sample container is in. And the reason for that is that you want to make sure you can separate what is actually the molecule absorbing different frequencies of IR light and what is the container that the molecule is inside of that's absorbing light. So the reference allows you to figure out that difference. And then there's some processing that happens. It's usually connected to a computer via USB, and then it produces an IR spectrum, which will look something like this. Oh, isn't that beautiful? There's so much rich information in this picture, if only we could understand what it all means. So first of all, at the top, you'll notice there's an x-axis that says micrometers. Forget that. I've never seen any IR spectroscopy that uses units of micrometers, so you usually won't see any micrometers in the picture. More commonly, you'll see wave number. Wave number is a way of measuring frequency. It's 1 over the wavelength, so that is a frequency measurement, and so that the higher the wave number, meaning the more we go to the left, the higher the energy. So increasing frequency of light. Okay. And that's going to be increasing to the left. And then on the y-axis, we have the transmittance. Transmittance is the percentage of IR light that's making it through the sample. So if the transmittance is 100%, and notice none of the transmittance is actually 100% because some of the light always gets absorbed either by the container or something like that. It's never perfect. But if the transmittance were perfect 100%, that would mean that all of the IR light made it through the sample. And on the other hand, if the transmittance were 0%, that would mean that all of the light of that frequency was absorbed. And what you can see is that most of the IR light passes through pretty much unaffected, but that there are certain regions where the IR light is absorbed strongly and doesn't make it through the other end, and there's these distinctive peaks and patterns. What is causing the IR light to be absorbed at these very specific frequencies? It's the presence of bonds inside of the molecule absorbing that light. So, how can we interpret this figure? Well, before we talk about interpreting this figure, I want to show you one other hint that's going to help us to solve problems, because pretty soon what's going to happen is I'm going to give you an IR spectrum and a bunch of compounds, and you're going to have to pick which one matches the spectrum. Sounds impossible, but I promise you it's a lot like being a detective. It's pretty fun. Okay, but before we get into that, I want to mention one more thing, which is the degrees of unsaturation. So in this class, we will use IR plus degrees of unsaturation to solve structures. That is our goal. And this is a big part of organic chemistry lab, because when you make something in the lab, a new compound, you need to be able to prove the structure of it. So degrees of unsaturation helps us solve the structure. So DOU, degrees of unsaturation, is equal to the following formula. 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens and then minus the number of halogens, which we'll abbreviate as X, all divided by 2. So that's the mathematical way to calculate the degrees of unsaturation. This mathematical way is useful if I give you a chemical formula like C6H12, blah, 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 blah. You can use the degrees of unsaturation formula to figure out the DOUs of that formula. But let's say I give you a structure, there's a faster way to determine the degrees of unsaturation. It's equal to simply number of pi bonds plus number of rings. That's a really easy way to determine the degrees of unsaturation if I give you the structure as a picture. All right, let's do a couple examples of this, and then we'll see some examples of how we can use IR spectroscopy in conjunction with this to solve structures. So let's say I give you the formula C9H8O4. Let's apply the formula. So it's 2 times the number of carbons, so it's 2 times 9, plus 2, always plus 2, plus the number of nitrogens, of which there are 0, minus the number of hydrogens, of which there are 8, and then minus the number of halogens, of which there are 0, all divided by 2. You do the math on the top, and you'll get 12 divided by 2 is equal to 6. So the degrees of unsaturation for this compound is 6. Turns out the compound that I was thinking of here is aspirin. So let me draw the structure of aspirin. Okay, this is the structure of aspirin. So CH3 here. And so we can look at the structure and figure out the degrees of unsaturation by just counting the number of double bonds or pi bonds. So we've got 1 pi bond here, 1 pi bond here, 1 pi bond here, 1 pi bond here, 1 pi bond here. That's a total of 5 pi bonds. So 5 pi bonds. Plus, how many rings do we have? I just see the 1 ring right here. So 5 plus 1 equals 6. So we can confirm then our degree of unsaturation is 6, either by using the formula or by looking at the picture. Notice that the formula doesn't have any spot to plug in the oxygens. The formula doesn't care about how many oxygens there are. So there's no spot in the formula here to enter the number of oxygens. So the fact that there were 4 oxygens was irrelevant to our formula. Let's do one more just to drive the point home. Let's say we have the formula of C11, H15, and O2. Okay, let's apply the formula. So 2 times the number of carbons, so 2 times 11, plus 2, plus the number of nitrogens, there's 1, minus the number of hydrogens, minus 15, minus the number of halogens, there's 0, all divided by 2. I'll do that math on the calculator. I get 10 on the top, divided by 2 on the bottom, which is equal to 5. Let's take a look at the structure of this compound and confirm. So the compound I was thinking of was this. Sorry, messed up my drawing here. There we go, that's better. Okay, so let's go ahead and count the pi bonds. So if I count the pi bonds, we have 1, 2, 3 pi bonds. And then go ahead and count the rings. We have 1 ring here and another ring here, so there's 2 rings. Add that up and we get 5, matching our calculated method. So whether you use the picture or the formula method, either way you should get the same result for degrees of unsaturation. And this is free and easy points on any exam. By the way, this compound is MDMA, methylene deoxymethamphetamine. It's actually an illegal drug. It's ecstasy. So you sometimes maybe hear about that in the news. So this is the structure of ecstasy. All right, so keep in mind how we calculate degrees of unsaturation, and now let's take a look at how to use IR spectroscopy. So if you look in your textbook, you'll find in the IR spectroscopy chapter this. To me, this is not the way to learn IR spectroscopy. What you're seeing here is tables and tables of values that kind of go from top to bottom and just talk about the different types of bonds and the different absorptions. No, we're not going to do this. This is too much. It's not intuitive. It would take too long to go through the whole list. It's kind of like reading a dictionary. It's boring. Is there a better way to interpret these IR spectrums without looking at these tables and lists and making comparisons? Absolutely there is. And I found this amazing picture online. I want to give credit to the author, John. I don't know his last name. It just says John. So thank you, John, for this. I use it in all my classes. So let's go through. It's kind of like a comic book. So we start up here with this idea. It talks about observations and inferences. And we do this all the time in our lives. We will make an observation, and then we'll make an inference or a conclusion about that. So for example, if you wake up in the morning and you see puddles and worms outside, that's an observation. But you can then infer that, oh, last night it must have rained. Right? We see evidence of something, that's an observation, and then we make a conclusion. Interpreting an IR spectra is the same way. We see, instead of seeing puddles and worms, we'll see an IR band, which is another word for like a peak in the IR, of a certain size and shape. And then that leads us to say it's probably that functional group, because that's what IR spectroscopy tells us. It tells us which functional groups are inside of our molecule. It tells us our molecule has an alcohol, our molecule has a ketone, our molecule has an amide. So it's, of course, it's really important to know all the different functional groups. You should already know that by now. Now, in the textbooks, they just list it from top to bottom, like this. It's not a useful strategy because some features are more important than others. Some clues are bigger than others. It would be like going to a crime scene and dusting for fingerprints when the killer left his ID on the ground. It's not efficient. We want to go over, we want to make sure that our effort is being spent wisely. We don't want to spend all this time digging over little tiny clues when there's a huge red flag right in front of us. And unfortunately, the tables in the textbook kind of take us down that path of, let's look at every little thing instead of noticing the big red flags. So we're going to go through the big red flags, and there's an order that I want you to look at when you look at an IR spectrum, and that is number 1. The first place you want to look at on an IR spectrum is the region between 3400 and 3200. This area gives you the most information, and you want to look for one of 4 patterns. You want to what I like to do is draw little eyeballs above here and a nose and pretend it's like a little guy above the spectrum, above this region of 3400 to 3200 wave numbers. And then if you see the little guy with his tongue sticking out, that tells you you have an alcohol. And if you see a vampire with double fangs, that tells you you have a primary amine in your molecule. If you see a poor little vampire with a knockout fang, that can mean one of two things. You either have a secondary amine, that is a nitrogen with one hydrogen attached, that's a secondary amine, or a terminal alkyne, which is you have an alkyne with a hydrogen attached on one side of the alkyne. And the last thing you want to look for is a hairy beard. If you see a hairy beard under your dude, then that tells you you have a carboxylic acid, which is the COOH structure, okay? So that's the most important place, and I want you to look at that region first. It's towards the left side of the spectrum. So let's see if I have an example here. We can look back at, I'll have an example coming later. Okay, we'll just keep that in mind for now. The second region I want you to look at is the area between 1800 and 1650. And in this region, you'll oftentimes see a single peak there. And it's not so much the shape of the peak, but the exact value, the exact wave number of that peak that tells you what kind of structure it is. And this area is referring to the CO double bonds. So this is where you find the CO double bonds. And so CO double bonds exist in a lot of different functional groups. We have CO double bonds in acid chlorides, esters, aldehydes, ketones, acids, and amides, and they all show up at a slightly different area in this region. So you want to kind of look up, if you see a peak in that region, that tells you know you have a CO double bond, but you want to look at the exact value and compare it to this chart. And so we'll do that in a second. One thing to keep in mind, and this little picture is kind of cool, kind of mentions it, which is that depending on the environment of the CO double bond, there can be some modifications to the actual wave number. So for example, this is an ester, and we know that esters show up at 1735. Well, if the ester is in a strained ring or conjugated through the oxygen, that can shift the wave number up a bit by like 30, so that instead of being at 1735, it may be at 1765. So just be aware of that possibility. And if you want, we can talk more about why this is the case. But for now, just remember that strain or conjugation through oxygen can affect the wave number by increasing it. Similarly, if it's conjugated through carbon, that can actually decrease the wave number and cause it to the peak to appear more to the right. So just be aware that the local environment does affect that wave number. And you won't see too many examples of this, but I just want you to be aware of it. Okay, the next area I want you to look at is at the 2200 area. If you see a little baby peak there, it kind of looks like it's in the middle of nowhere, because usually there's nothing around that area. Usually that area is completely blank. So if you see something at 2200, that tells you a lot of information, and that tells you have a triple bond. So either a CC triple bond or a CN triple bond. Okay. And then finally, you're not going to worry about this one so much. That is for a more advanced class, so don't worry about this one. The next thing you want to look for is the area right at 3000. I like to draw a line right at 3000. If you see stuff only to the right of the line, that tells you generally you only have single bonds. If you see stuff to the left of the line, that tells you usually have double bonds, like alkenes. And one last thing I could mention here, the aldehyde. You can usually look for a peak around 2700. You'll sometimes see a little something there, and that is evidence of an aldehyde, but it can be very small and sometimes it's hard to see. Okay, that's why it's one of the last things you check for, because the aldehyde, it's hard to tell. Okay, there's a lot of information here, so let's go ahead and apply everything we've learned to do some examples, and then I'm going to send you on to do your worksheet where you'll have a chance to answer some questions and turn that in for points. Okay, here's an example question. I've given you a formula and an IR spectrum, and there's also some possible answers. So because I've given you the formula, we can calculate the degrees of unsaturation. So let's go ahead and calculate the degrees of unsaturation. So 2 times the number of carbons, so there are 5 carbons, plus 2, plus the number of nitrogens, there's no nitrogens, minus the number of hydrogens, there's 10 hydrogens, minus the number of halogens, there's no halogens, all divided by 2. Do this math on the calculator, we get 2 times 5 is 10, plus 2 is 12, minus 10 is 2. So this gives us 2 over 2. So our degrees of unsaturation is 1. Now let's look at our possibilities here and eliminate any of these options that does not have a degree of unsaturation equal to 1. Because if the degree of unsaturation is not 1, then it can't possibly be our answer because it doesn't match the formula. So looking at the first compound here, how many pi bonds does this compound have? 0. How many rings does it have? 0. So the degrees of unsaturation for that compound is 0. So it can't be this. So I'll put an X through that. Next compound here, it has 1 pi bond and no rings. So it does have a degree of unsaturation of 1. So that is a possible candidate. Next up here, this has no pi bonds, but it has 1 ring. So it has a degree of unsaturation equal to 1. So that is also a candidate. This one here has 1 pi bond, but no rings, so it's also a degree of unsaturation of 1, so that's also a candidate. The last one here has 2 pi bonds plus 1 ring, so that's a degree of unsaturation of 3. That is not a candidate. So it's going to be between 2, 3, and 4 for our options, either 2, 3, or 4. Now, option 1, notice that it has the alcohol functional group. The alcohol functional group, we can tell if a molecule has that if there's a big tongue around the 3400 region. Is there a big tongue over here? No. There's no big tongue. So that's going to be a no for me on that compound. So now it's just between these two. What is the one distinguishing feature between these two compounds? For me, the big thing to look for is the CO double bond. Remember that the CO double bond, specifically the ketones, have a sharp peak in the 1700 region. So looking back here at our list, the ketones show up at 1715. I know it's hard to see, but it says 1715 there for ketone. So let's look at our spectrum. If we see something at 1715, then we know it's option 4. If we don't see something at 1715, then we will say it's option 3. Let's take a look. Oh, there's something there at 1718. That's close enough. So I'm going to go ahead and say this is our answer, and that is indeed correct. All right, let's do another one. Okay, we've got a formula. Let's go ahead and calculate the degrees of unsaturation. So we've got 2 times the number of carbons, so 2 times 5, plus 2, plus the number of nitrogens, there's 1 nitrogen, minus the number of hydrogens, there's 13, there's no halogens, divided by 2. Do that math, and we get 0. Get 0. So that means we have to look for possible compounds that have no degrees of unsaturation. That means we can only consider compounds that have no pi bonds and no rings. So I see some molecules with rings. I'm going to go ahead and cross those out because those can't be right because that's a degree of unsaturation. Also, the last compound there has a ring and some pi bonds, so that can't be right either. So immediately, just by using the degrees of unsaturation, we've limited it down to 2 possibilities. Now, one thing to do, where's the first place we look? We look at this region here. What do we see? Do we see a tongue? Do we see a beard? Do we see vampire fangs? We see vampire fangs. We see the double little fangy thingies. That tells us we have a primary amine, which means a nitrogen with 2 hydrogens attached. There's the vampire fangs right there. So, since our options are either this or this, which one seems more likely? Vampire fang tells us it's a primary amine. This is a primary amine. This is a secondary amine. So that means the answer must be this one. One way that I help me remember it is if I see 2 vampire fangs, that means I have 2 H's on my nitrogen. Let's do another one. All right, this formula is C3H6O2. So we'll go ahead and write 3 times 2. I don't know why I keep writing like that. So 2 times 3, 2 times the number of carbons, plus 2. plus a number of nitrogens. There's no nitrogens. Minus 13. Sorry, not minus 13. Why did I say that's for the last one? Minus 6. Divided by 2 is equal to 1. So we have 1 degree of unsaturation. So we can go ahead and cross out any of these molecules that have other than 1 degree of unsaturation. But if I look at all these molecules, they all have exactly 1 degree of unsaturation. This has a pi bond, this has a ring, this has a pi bond, this has a ring, this has a pi bond. So we can't eliminate any of these due to the degrees of unsaturation. However, we do notice a hairy beard. You see how it comes down so much, and that's kind of creating that hairy beard appearance? That tells us we have what functional group? Carboxylic acid. Looking at all of these structures, there's only one carboxylic acid present, and that's the first one. This is not a carboxylic acid. 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 Be careful. Even though it looks like it could be a carboxylic acid, the OH is one too many carbons away. This is the only carboxylic acid. So this is our answer. So the hairy beard told us everything. All right, next one. Oh, wow, this is challenging. I did not give a formula. So we can't calculate degrees of unsaturation. But one thing I noticed right off the bat, we've got a big tongue here, don't we? We've got a big tongue here. So that means we should limit our answers to only the alcohols, because remember, the tongue represents an alcohol. So I'll go ahead and cross out anything that doesn't have an alcohol. So this does not have an alcohol. Careful, this molecule here is a carboxylic acid. It would look like a hairy beard, not a tongue. So I'm going to cross that one out as well. So it comes down to 1, 2, or 4. Now, the distinguishing differences between these compounds is compound 2 has a double bond and compound 4 has a triple bond. If your compound has a double bond, the great way to tell for that is to draw a line right at 3000. So I just drew a line right at 3000. If you see stuff right above 3000, that tells you you have a double bond. But if we look over here right above 3000, we don't see anything there. So to me, that eliminates this possibility right here, because there's nothing right above 3000. There's stuff right below 3000, and that just tells you single bonds or triple bonds only. Now, to tell if you have a triple bond, there would be two ways. Since this is a terminal alkyne, there's a H attached. Remember that the H attached to the alkyne looks like a single knockout vampire fang. We would see a sharp peak right around here. However, it's possible that that peak is there. It's just being hidden by the alcohol tongue. That's something you got to think about. Potentially, it could be hidden by the tongue. It could be buried in there. We wouldn't see it if the tongue was too big. However, there's another place you can check for an alkyne, and that's around the 2200 region. Remember, around the 2200 region, I call that the desert, and there's usually not a lot of stuff there. You'll see a peak there for the alkyne, for a CC triple bond or a CN triple bond, but we don't see anything there. So that eliminates this possibility. So that means our final answer is number 1. It's an alcohol, but there's no evidence of a double or triple bond. All right, 2 more examples left. Again, no formula given, and one thing I noticed in this right off the bat is we don't have any tongues, we don't have any beards, we don't have any knockout fangs. We see a little bit of stuff over here, but it's not really much. I also noticed we don't have anything right above 3000, so that tells us probably no double bonds. But I do notice some strong double peaking here happening around the 1700 range, and that tells us that we may have 2 different types of CO double bonds. So we should eliminate any possibilities that do not have 2 CO double bonds. For example, this compound here has only 1 CO double bond. This compound here has only 1 CO double bond. This next one here has 2 CO double bonds. This one here has only 1 CO double bond, and also it has an alcohol. It has an alcohol here. We would see a big tongue if this were the answer, so we know that's definitely not it. And here's another one with 2 CO double bonds. So it's going to be between 3 and 5. So for now, we can recognize that we have a ketone and an ester. And in the last one, we have a ketone and an amide. Okay, now let's look at our table and see where ketones, esters, and amides show up. Okay, so the ketone shows up at 1715. The amide shows up at 1690. And the ester shows up at 1735. So now let's take a look back at our question here. Okay, the two peaks we have is one at 1745 and one at 1718. So remember, our ketone shows up at around 1715. Our ester was like 1735. And our amide was like 1690. So which possibility matches most closely with these numbers? We have a 1745. It's pretty close to being the ester. And we have 1718. That's definitely the ketone. So if we had the last option, we'd have a 1715 and a 1690. But since we have a 1715 and a 1745, it's definitely closer to this option. So we'll go ahead and say this is our final answer, and that is indeed correct. So we had to look very closely at the exact numbers there to help distinguish the ester from the amide. All right, let's take a look at one more, and then I want to turn it over to you to try solving the worksheet and turning that in. Which is which? So two spectrum. Oh gosh, I see that I put the names here. Don't look. I better hope I don't do that on the exam. You better look for that. Okay, but we can still figure it out. And what you'll notice is that one of these alkynes is internal. The other alkyne is terminal. So the best way to tell these two alkynes apart is to look for the H that's on the alkyne. Because remember that terminal alkynes have a hydrogen attached to them, and that hydrogen appears around 3000 as a single knockout fang. So what you can see here, we have something around our 3200 area, and that's going to be corresponding to the alkyne CH bond, which is a vampire knockout. We can also see the CC double bond evidence right here in that desert region around 2100, 2200. So definitely this alkyne is represented by this spectrum. The top spectrum has no vampire knockout fang, and that makes sense for the top compound because there is no hydrogen attached to that alkyne. It's got a carbon on either side. So you only would see the vampire knockout fang when the alkyne is at the end of the molecule, what we call a terminal alkyne. We also, interestingly, notice that there is no signal for the CC triple bond at 2100. Why not? Why would there... This is an alkyne, isn't it? And we usually see evidence of an alkyne at 2100. I mean, we saw it for this compound. Can you think about why there's nothing there despite this compound having a triple bond? Pause it if you want to think about it, because I'm going to tell you the answer in 5 seconds. IR inactive. So this molecule, this top molecule here, is symmetric. So there's no polar bond. So that's why that bond is invisible by IR. So no C triple bond C band because IR inactive due to symmetry. So remember that. If the bond is not polar, it's in a highly symmetric environment where it's the same on the left and the right, usually that signal will be invisible in IR. And that can actually help you distinguish between two possibilities. Okay? All right, so we'll leave it for now on that. Make sure you download the little guide, the IR spectroscopy guide. That's this sheet of paper here, which I've attached. Thanks again to John. And take this handout. I suggest you either print it out or have it on your computer screen, and then try and solve the lab worksheet. And you can answer the questions. You can match the spectrum to the compound, turn that in, and get some points. All right, good luck. And I'm here to help you if you have any questions.